My name is Avkash, and in this tutorial, we are going to extend our knowledge from graphs to graph neural networks. This tutorial is the extension of our previous tutorial where we have learned the basics or the fundamentals of the graph and their applications using NetworkX Python library and using the Python programming language with some of the functionality available in the PyTorch geometric or PyG. In this tutorial, we are going to cover these important aspects. Here is a list of content or the topics which we are going to cover. We look around various graph representation types. Then we will focus on node embedding and the node embedding space. We will learn how to apply convolution to the graph similar to images. Message passing, we also look the variety of data sets available in the PyTorch geometric, how to understand those data sets. So you could prepare yourself to perform various graph neural network tasks such as classification, node similarity, etc. We also try to visualize our network using tSNE and NetworkX, and once our graph neural network model is ready, we will learn how to apply the Graph Neural Network Explainer modules. Because we have already covered Adjacency Matrix previously, so we are going to cover the Incidence Matrix, Degree Matrix, Laplacian Matrix, how to calculate the Laplacian Matrix. Then we will learn how to display the graph, which we are using as an example to build the graph using the NetworkX library. So here you could visualize your own graph, which we are using as an example. After that, we are going to learn the bag of nodes method, the idea of walking a graph, how you could walk a graph from one node to another. Then the concepts related with graph neural networks, what is the role of Laplacian matrix, then the image representation method, basically the convolution method such as the locality, aggregation and composition, the way these concepts work on images. We are going to learn that how these three concepts are going to apply on graphs. And that's where the concept of node embedding comes. So we are going to learn that what is node embedding, how you can apply the convolution in the node embedding, means how you can apply the locality, aggregation and composition on the node embeddings. And that's what we are going to learn in our tutorial. Finally, the concept of message passing, the message passing with propagation is all part of discussion in this tutorial. Once we understood these concepts related with graph neural networks, we will jump into the programming part of graphs, where we are going to learn the various ways to build the graphs with the NetworkX Python library. And after that, we will spend significant amount of our time to understand the data sets for graph. We are taking the one data set, Karate Club, so we can prepare ourselves to build the machine learning models around it. In the next Jupyter notebook, we extend our knowledge of Karate Club data set and we perform a GNN experiment. And in this graph neural network experiment, we learn that how the given data set classify its node in 4 different groups and how we can get results something similar to this, where the node are classified depending on other similar nodes. In the very last node classification experiment using graph neural networks, we use the Cora data set available in PyTorch geometric, and we learn initially that how the initial node are grouped together across 7 different classes or the types. And after we build a graph neural network of 2 layers, we learn that how these nodes are assembled like this. And at the last, we use the GNN Explainer module, which is part of PyTorch geometric, and where we learn that using the GNN Explainer, we can identify what were the reasons so that a particular node is classified as part of a given group. So this tutorial is packed with lots of graph neural network specific knowledge. Some of the knowledge is given through the slides by explaining some of the important concepts required for you so that you could prepare yourself writing better graph neural network experiments depending on the problem you are working on. So let's get ourselves started. In this section of our tutorial, we are going to cover the adjacency matrix, incidence matrix or the relation matrix, degree matrix, and Laplacian matrix. Bag of notes will come little later. So adjacency matrix, which we have already covered earlier, so let's review it one more time. So adjacency matrix is a 2D matrix. So it means the total number of nodes times total number of nodes. So A equals n times n. So it's always going to be the square matrix. And if you do not have weight, then it could become a binary matrix. Now here is a weighted and undirected. So if you have weights, you will provide the weight. If there are no weights available, you will give the negative value to it. 0 could be the weight value as well. That's the reason we are using -1. Here we have weighted and directed. Differences between directed and undirected is that in undirected, if you see here, A to B is 12, but B to A is not 12 because A to B can satisfy the value between A to B here. However, if we look into directed, we are specifying it correctly that A to B is 12 and B to A is 34. So next we have unweighted and directed. Here the directions are there, so A to B is true and B to A is true. Rest values are false. You convert it to 0 and 1, where 1 is true and 0 is false. Next, unweighted, undirected, very simple. Here A to B is true, B to A does not need because there is no direction built into. Same, true and false can be referred as 0 and 1. Here, the adjacency matrix, when we have it, we can understand a little more deeper to know about the relationship or the adjacency between the nodes. So if the adjacency matrix is A and you want to know the path from C to D, you can get from C to D, there is no direct connection, but C to E, E to A to B, and B to D. You can create a path. You can build the adjacency. If you choose the levels and hop, you can say, oh, my levels are only 2. Then it will make sure that can you get to D within E and A. If you cannot get, it means you do not have path. However, the labels or hops are available all the way to wherever you would want. B to C, there is no way you could go B to C because there is no path exists to go. That's why it's a directed. Same thing, if you look into A to F, you do have path A to C to E to F or A to C to F. So there could be 2 paths, A to F, and which is the shortest path. Now you have a competition among the shortest path. So after the adjacency matrix, now we can look into the incidence matrix. So incidence matrix referred as I, and it is designed to show the value between the edges and the nodes. If your edges are labeled, then you use your edge labels. If edges are not defined by label, then you can use the notation of AB. E2 will become AC. So incidence matrix is basically just if there is a to B, E1 is a 1, if B to A is also 1 because of undirected graph. So you are representing 1 and 0. If the connectivity between 2 nodes, 1, if no, it's 0. Now if we look into the incidence matrix for the directed graph, your values are -1, 1 and 0. 0 means there is no connectivity. So if you look into E4 here, E4, E4 is only between E and F. So E4 has nothing to do with node A. That's why it's 0. However, the relationship between A to B is -1 to 1. It means the node to outward, if the node to outwards direction, it means node to outward direction, then value will be -1. And if this is the node and if the connection is coming this way, then it will be inward. To node to inward connection, then this value will be positive. For that reason, A to B, A is negative and B is positive. Same thing between A to C, the A is negative and C is positive. And incidence matrix is going to be used as the total number of nodes times total number of edges. So after we have covered incidence matrix, the next in our line is degree matrix. So degree matrix is also called as diagonal matrix. Diagonal matrix means you only have the value of diagonal. Just looking into that, it tells that the connectivity among the node, how many connections are coming to this node. We look into A, there are 2 connections, but if we look into the B, there are 4. Reason 1, 2, 3, 4. So when a node has self-loop to itself, then that considered as a 2 connections. That's why you see the F has 5. 1, 2, 3, and these 2. So these are the 5 connections. So you can get an idea that the degree matrix is just basically the diagonal value of a matrix which shows the total number of connections at that. So degree matrix is always going to be used as the nodes time nodes, but only the value from the diagonal are represented here. Next is the Laplacian matrix. It's a very important concept because we have to use this thing when we are building our graph neural network. So what is Laplacian matrix? So Laplacian matrix, also called as a graph Laplacian matrix, and it's used to measure the smoothness of the matrix. So when we talk about the smoothness, we are really looking into the from image perspective, that smoothness curve of that image too. A Laplacian matrix is denoted as a L, where L equals to D minus A. Means you take the diagonal matrix and you subtract the adjacency matrix. What you get is basically your Laplacian matrix. So L equals to number of edges connected to the node. So the node, how many connections are there, minus the adjacency matrix. How many total adjacent value available for the node, because the adjacency matrix is also a squared matrix. So it's also n times n. So here we look into this example where you could see that this is the same graph which we have studied again and again. So the Laplacian matrix D minus A, so this is our diagonal value. So 2, 4, 3, 2, 2, 5, we have already did, and here is our adjacency matrix. And because of the self loop into the B, we are using the value 2 here. So as you could see here, the A to B is 1, B to A is 1, and B to B is 2, F to F is 2. So these are the self loop which considered as a 2 connectivity. So that's why we are using 2 here. So you can get, this is our adjacency matrix, this is our degree or diagonal matrix. So when you subtract this value, you are going to get this result, so D minus A. And we will actually use the NetworkX library to prove this everything correctly. So now if we have this graph and we would want to show this graph like this way, we are going to do the full exercise in the Jupyter notebook, and we make sure that we have built our graph exactly what is shown here to this format, which shows the edges plus fully classified representation, because there are 6 nodes, all 6 nodes belongs to 6 different classes. We do not have defined a class framework for our nodes. So everything is independent to each other. So here I already have Jupyter Notebook up and running, and I'm using the Google Colab. So we are importing the NetworkX, which is pre-built. And here in this example, what we are trying to do is that we are building a very simple 3-node graph with 2 edges. So this is a 3-node graph which 2 edges is undirected graph. There are no direction, and we have referred the node color. We have also asked to with labels true, but there are no labels here, and it will come later for you. If we want to create a self loop here, so we are creating a self loop with 3, and we can build. Now you could see that there is a self loop available. If this graph is not weighted, this graph is not directed because we haven't provided any weight to it. However, if you would want to take this graph and you want to look into how its representation look like, that's the same graph G which we have created, that's its representation. Next, we are taking this graph and we are adding 3 self loop, and here you see that we are adding the weights to edge. Let's represent it. Now you could see here that this is the graph where we have 3 self loop and 2 nodes, and here you could see that this graph is not weighted, this graph is not directed. So we already know, and here we do have a weight, and I'm coming into there. So if we try to take this graph and you represent it, you can see that weights are referred here because 5 weight is referencing to here between 3 to 2. So here 3 to 2 and 2 to 3. So that's why you are seeing this weight 5 to 5. However, the value is saying that is weighted is false. Let's try and change it to weight 3, call it 6, call it 9. Let's build it. Now you see that weighted is true. So if you would want to create the weighted graph, you need to make sure that weights are defined to all the nodes. Otherwise, the is weighted value will always going to be the false. So once we did add the weight to all the nodes, now it's a true weighted graph. And if we try to represent this with this value, now you are getting a different matrix value. So make sure that you have that clarity in your mind, and then when you write your code, that's also represent correctly. Now, once we build these graphs, some graphs, now we can get what we have just learned. So incidence matrix is I dot 2 dense. It means the matrix representation of our incidence matrix. We have already looked into incidence matrix was the edges and the nodes. So edge and nodes and connectivity. So it just shows the connectivity. So if you look into here, you are getting connectivity A to B and B to C. And if we look into our graph, you can see A to B or B to C, 1 to 2, 3 to 2. And because this is undirected, so that's why it's represented. So hopefully that clarifies you our incidence matrix. Now, if you would want to take the same matrix and you can say, oh, I need to get the adjacency matrix. Very quickly, you can create that one too. You just say A equals nx dot adjacency matrix of G. And then once you have A available, then you take that A and then you can say 2 dense, and that became your adjacency matrix. And adjacency matrix is the node times node. So you are going to get a square matrix of 3 of 3. And here you are getting the weight. And if you look into here, this is the matrix and here is your adjacency matrix. And in this matrix, we are going to create the 3 to 1, and we just call it 10 weight and 110, 1 5 10. And let's build this matrix. Now you can say 1 2 3 we have built. So this is the all, if we 1 to 2, 2 to 3, 3 to 1, 1 is connected with both, 2 is connected. So this is a complete graph. We have connected all the nodes with each other, and that's why you see this graph is also the directed graph. So here we are using directed graph. That's why it's a directed and weighted. Every node has its, every edge has its weights, and every node is connected with remaining all other nodes. Now if we build the incidence matrix, I dot diagonal. So this is just a diagonal value. Here is the I representation. In the previous matrix, which was the G, if we would want to get the diagonal, we can exactly use the same way. We can take the matrix, whatever we have I, we can take the A, because diagonal you can collect everything. So for example, if you would want to take this A dot diagonal, and you will get 965. So diagonal or degree matrix can be represented for every given matrix because you just need to get the diagonal value. Now for the second matrix which we have just created, this one we are building the adjacency matrix. So here is the A and here is our adjacency matrix look like for this. Now we are going to get the Laplacian matrix, and it's really very simple because now you just need to use the NX, means the NetworkX library, and Laplacian matrix. And here you see that our G, which is very recently we have defined this one, and this is a directed graph. So you are getting the error here which shows that not implemented for the directed type for that. Okay, and here you could see that L is not clear here. Now what we could do, we can come back here, and which is the undirected graph. We run this. So now our G is the undirected graph. So what we could do, we take this whole thing, we come back, we have two options. Either we change this to directed graph because we need a directed graph to perform the Laplacian, or we can use the previous graph here. So when we are trying to build the Laplacian graph here, we could add this cell and we can say we want to use this graph as a undirected graph. So now we try to run the Laplacian matrix and we will get the value of L here. Now we can get what is in L and we can get the L to dense. So this is our Laplacian matrix. So Laplacian matrix is D minus A. So once you get the idea of the adjacency matrix, here is the A dot data shape. What's the 3 by 3? And then you can get the representation of A. And here the G2A edges and nodes. So here you could see there are the edges and there are the nodes. So now if you have a graph which you would want to put together with the labels X true and font color white, let's see what is here. So here what we are trying to do is that here we want to set the graphs with a particular class. So here you see that we have this graph G which we have created, and here what we are trying to set is that we want to put the graph based on some values. So you look into a graph, as you could see here that there are A to G, so A, B, C, D, E, F, G. So A, B, C, D, E, F, G. So there are 7 nodes. And if you look into A and H are in one group and everything else in another group. So you have the A group, you have the H group, and you have remaining group. If you use the D, for example, now if you run this graph again, now you are getting everything between D group because that's the middle group. If we add one more here, you are going to get the D is a different color and then rest are the other. So now you have 4 groups. If you try to make one more resolution here, you can say G and you call it 0.9. So you get 1, 2, 3, 4 and 5 color. So that's the reason you are getting the 5 different classes. So if you have a graph which is based on group, you don't need to create these groups. You can just put a group, you can pass the group value here and your graph will be created based on that class architecture or class notation for your nodes. Here we are using the directed graph, and as you see here that edges are, if you look into our previous graph, we have edges here. So we cannot use the directed graph. So if we just build this graph, here you could see that we have added some self loop in this graph. So there are the BBFF, we have added the self loop. We have also put the representation of these graph value, and this graph is not weighted, is not directed graph. Now we look into the adjacency matrix for this. It's 6 by 6 graph, diagonal for your graph. And here is the Laplacian matrix. And this is how the Laplacian matrix look like for this graph. In our examples, we have used this graph again and again. So it would be good if we use this graph to build a graph in the NetworkX. It means taking the concept which is in image here and convert that everything to a real actual graph code. So here we have all the graph edges. So you see A to B, B, A to C. So all the edges which we have here, including these two self loop, we have defined here. So these are all the edges. And then for now, I would suggest you just we can block this code. Okay, so here is a list of all the edges we have, and we are building a graph. So let's build the graph, and this is what it really look like. All the edges and all the nodes. If we try to build again and again, you might see a variation. However, this is the exact graph. So F and B edges have the self loop and rest of the nodes are connected. So this is not a weighted graph and it is not a directed graph. Now, because we want to make sure that all the edges we have, they actually belong to different groups. So you see here A, B, C, D, E, F. So in order to make sure they are coming out from different classes, we have created this value map. And what this value map is that it takes all the nodes and put them in different classes. And we take this node color which we want to use based on the values we have set here. And if we try to render our graph, now you are going to see that all these 6 nodes are in 6 different classes. However, if you look into our graph, A, F, same color, C, D, same color, and B, E, same color. So if you want to put in 2 groups, because right now the nodes are in 6 groups. So you can actually change the value. If you see A and F are same, so you can say A and F is 1, B and E is 2, so B and E is 2, and C and D, we can give them 3 value. And if we try to build this way, you are going to get that B and E is same, D and C is same, F and A is same, because we have created a certain kind of class with them. So our representation can be built based on these classes. Now, if you are looking this graph, and as you see here that our graph is not a directed graph. But if you would want to see the same graph in a directed way, what you could do, you can just use this trick, and here you are not changing the graph. You are seeing the graph in a directed way. Your graph is still undirected. And as you could see here, I just use only draw method, and that add the graph to the directed. We haven't really used all that code to beautify it. However, if you would want to beautify it, you could actually use the exact same code here, because most of the values will work. You take this code and then you take this G dot directed, and the same graph will become a directed graph, but your graph is still same because there is no change happen. Because if you try to run this graph with G, you are going back to same undirected graph because your graph is still undirected. So if I come back to here G, your graph is undirected here. So doing this way, you can see a graph based on a directed as the edges are defined from source to target. Next, you are creating the incidence matrix for your graph G. Now we want to render the edges here. So E1 to E7 are the edges, and the B self loop and F self loop is also like a B is E8 and F self loop is E9. So in this section, we are defining the edge labels. They are same as what we have seen in our image, and here are all the edges. So edge and edge labels are defined. Then we are just passing all the edges here, and rest of the code is designed so that we could get the labels or edge labels are also. So let me run it first. So it's the same graph. We just made it a little bigger so that we could see the labels clearly. And in order to see the edge labels, there is some extra code is really, and just draw NetworkX edge label, and then we are passing the edge labels and then talking that what the color should be, and edge labels has to be defined here. So we have already defined. Next comes the total number of nodes and total number of edges. And remember, the edges are 9 because we have 7 direct edges and then 2 self loop. So if you disable the self loop, you might not get that number. Now we are taking the directed, and here again, this is your NumPy and matrix G represented as a matrix. So whether you are using this or you are using undirected like as it is, as you could see here, everything is same. One difference could be that if you are using the graph where the weights are there, then everything changes. So based on our graph G, we are creating the adjacency matrix, and here is your adjacency matrix, and here the adjacency matrix look like. Now we can go look into our code where we have worked in past. So adjacency matrix is here. Here is the adjacency matrix, and here as you could see here that self loop are the 2, and self loops are counted as a 2 here. So here if you look into the adjacency matrix, you will not see 2 here, 2, 2, you are only seeing 1 because the undirected graph is going to return only 1. Directed, that's why you are not seeing these value as a 2. If you look into the diagonal is going to be 0, 1, 0, 0, 1, and here look into 0, 2, 0, 0, 0, 2. So that's a big difference you are seeing here. But because we know these are 2 added, and later we will look into when the Laplacian will be calculated, b minus a, then you will see the correct values over there. So just I wanted to make sure you understand that part very clearly. And we do have a method called the generate adjacency list. So if you try to build this generate adjacency list, here you will get a, for the a, the adjacency is a b and c. For the b, the adjacency is db. So we can look into a, b, c. So for the a, definitely it's a bc. For the b, it's a and d and b2. So it's going to show db. For the c, it's a ef. For the C, it's a EF, the A is missing. So this does not work properly when you are trying to generate the adjacency list. So I have a better function which really shows not only all the edges but really clearly. So here is a method which is defined, and if you run this method where you say for given graph G, can you generate the adjacency list? And here we are getting a lot more clear and correct, and this method helps us. So for A, it's a BC. For A, definitely BC. For B, it should be A, B, and D. For B, ADB, because ordering can be changed. So that's why ADB, it's correct. For C, it should be AEF. For C, it should be AEF. And for D, it should be B and F. For D, it's a B and F. For E, CF. For E, definitely CF. And for F, it should be CDEF. So CDEF. So it means this is the way you can get the adjacency list for every node, and it may not be really correct one. So that's why I showed you math function, but I gave you the better updated function. Now we are generating the incidence matrix, and this is how the incidence matrix look like. The node degree matrix. Degree matrix is basically which tells you that how many nodes are connected for the diagonal. So you will look into this value, you say 243, 225, 243, 225. That proves you that the B2B is 4, F is a 5, which we are not seeing in the adjacency matrix. So then the Laplacian. So Laplacian equals to G equals to D minus A. So when we build our Laplacian, this is our Laplacian matrix. So we can look into this. So this was our Laplacian. So D and A, and if we try to go D minus A, this is our final matrix. So you are subtracting 2 minus 0 is 2, 0 minus 1 is negative 1, here 4 minus 2 is 2, and here 5 minus 2 is 3. So if you look into the diagonal, it's a 2, 2, 3, 2, 2, 3. You are looking diagonal 2, 2, 3, 2, 2, 3. So if you take this value and you say I want to get the diagonal of that, and here is the 2, 2, 3, 2, 2, 3. So you got the diagonal for that. And so we have quickly covered incidence, adjacency matrix, degree or diagonal matrix, and the Laplacian matrix. The next concept for us to understand is the bag of nodes. So the bag of nodes is a way to represent the node level features. The bag of node algorithm is very popular in some of the use cases related with chemical informatics or chem informatics area, where this Wiesefelder-Lehmann kernel algorithm is used to aggregate the information iteratively from the node's neighborhood. So if you are interested to learn more about it, I would suggest you to please visit this URL, and that will give you a lot more detailed information if you are interested in bag of nodes. Next in our list is the graph walking or the random walk to start. So what is the graph walking? So graph walking is a method to traversing all the graph through a connected node. So your graph is connected with so many edges, and you would want to walk from random node. You select a one particular node, for example C, and you say let's walk. Let's walk 2 level. C can go E to F, C can go F to D, C can go A to B, because it's a 2 level walking. If you choose B, you say 2 level walking, it can go B to A and C, or it can go to B to D. So B random walk has 2 options. C random walk has 3 options. F random walks has 3 options, but self loop is not really walk. But in that case, it can go FF and next. So depending on how many available connection a node has, that gives that node the opportunity to perform that many random walks. So random walk is a technique which is used to extract sequence from the graph from any random node perspective. And you use this method to train the escapegram model. And if you would want to learn the node embeddings, because node embeddings will be used a lot when we will talk about the graph neural networks. So if you would want to perform the random walk using the NetworkX and this given graph, you could do very easily. And for that, I have added in the same introduction NetworkX part 2 notebook, I have added the graph walking method. So here is our method for the graph walking. What it does, it actually just variable where we are passing the node. So which node you are interested to perform the random walk, and how many hops you would want to go. You want to go 2 hops, 3 hops, 5 hops, 10 hops, 100 hops, because depending on how big your graph is, you can actually go very deep. And here, depending on the path length, you are going from 0 to that much path, and then you are looking into the given node, all the neighbors. So here is the neighbors, and then based on that, you are performing the random walk. So this is our method, and here in our graph, because we are passing the graph G, which we have just created, because we are using G here. If you would want to make any graph, you can actually use here the graph value, and you can replace with this, and then you can pass the graph value here. So in this case, this will become G. So this is our method, and here is our graph. So in the G graph, what is the random value for A 2 level? If you say A to B, if you say 3 level, you are getting ABD, A to B to D. And if you look into our A to B to D, when you say A, I want to go to 5 labels. A, B, D, E, F. Okay, if we choose from E, for example, 5 label, it's a ECFDB, ECFDB. So we can look into ECFDB, ECFDB. So here, when we generate the walking, we see random.choice. So temp is a list. So we just select whatever is available in this temp. We just select one random node, and then after that, we just append that node, and that's what become your a node, and then you just keep walking through. And then finally, the random walk list is what you are getting the node value. So you get an idea that depending on which node you are interested, you can generate the walk. So there could be random paths can be taken, and that is come from random choice when you are selecting the list here. So for the E, the random will be whatever is available from. Okay, so if we try to run again, ECADB is this time change the path. So ECADB, I was expecting to go this path, like one side this way, one side this way. So ECABD, if we do random again, ECFDB. So this time we went ECFDB. So at least you get an idea that randomness is there when we perform the random walk. So if we would want to calculate the total number of walks depending on how many hops, how many deep level we would want to go, this method is going to help us. Here, as you could see, that we are looking into up to 1 level. Let's have how many walks? 1 level. From each node, you can have 6 level. Now you say, I want to go up to 2 level. You are going to get 12 walks. If you are using for 3, you are getting up to 3 level. You are getting 4. So here you can get an idea that how many random walks you are going to get depending on how many nodes you have. So we have completed the random walk portion of our tutorial, and at this point I would say that this notebook for the NetworkX and the graph related representation methods is all completed. So this notebook is saved, and it's also going to be available at this graph neural networks folder, DeepWorks. So now if you would want to follow this tutorial, you can follow it by yourself. Until now, we have studied graph as a collection of nodes and edges, and we have performed various representation techniques around that concept. But as soon as we talk about graph neural networks, we need to think graph little differently. It means we need to think graph as a neural network. So the journey from taking the graph and understanding it from the neural network perspective is the remaining part of our tutorial. So what is neural networks? We already know that neural network is a collection of input layer and output layer, and in between there must be one or more hidden layers. Here, as you could see, we have input layer X, output layer Y. In between we have 3 hidden layers, H1, H2 and H3. So in the neural network, the role of Laplacian matrix is to generate the smoothness of the image in 2D space. Same thing, we could use the same Laplacian matrix for applying the smoothness of the node or vertices in the graph. So we already know in convolutional neural networks we perform convolution. Mostly CNN is worked on your images. So image is a collection of pixels in X and Y plane. So you have columns of pixel and you have rows of pixels. Each pixel is represented X comma Y, which is like which row and column that pixel stands. Pixel has its own value. Now, depending on pixel where it is in that image context in X and Y plane, a pixel can be represented as a 2D fixed size grid, and depending on the pixel, now you have the neighbors. because if you have a pixel A, it has the three neighbors and with fixed location. So no matter what you do with image, the pixel A neighbors is going to be fixed there. Same thing goes with pixel B, or every pixel similar location as a B, because pixel B is not at a corner. Pixel A is a corner pixel. Pixel B is the not in a corner but not in the middle. And pixel C is the middle pixel. So everywhere you will see that there are three kinds of pixels. You have A, B, and C based on position. So depending on which pixel you are, you might have three neighbors, you might have five neighbors, or you might have eight neighbors, but their location is going to be fixed. And when we talk about the convolution on images, what we really do is that we perform three main functions. One is called the locality, second is called the aggregation. Locality and aggregation is combined together on every pixel, and then we do composition, which is the function of the function. So let's take a very quick look. You have image and you have a mask. Here we are using a 3x3 mask. So in the image, we start the mask, and then depending on our mask 3x3, for example here, the pixel of interest is the center pixel there. And depending on that, all the neighbors. So we have 8 neighbors. The contribution of the n neighbor, depending on whatever the mask reference is. So for the 3x3 mask, the contribution of the 8 neighbors, what defines the value of pixel of interest. So which defines the value for the pixel of interest. So as soon as you have a mask and you put top of the area in that image, that's immediate define the locality. Now your locality is fixed. Next, what happens is that you need to perform the aggregation. You multiply your mask coefficient to the all the pixels available in that mask locality, and you aggregate all of their sum. When you aggregate all of their sum, the resultant value will become the value of that pixel. So that's a new pixel value. And then you move the mask to next. Now you are into the next pixel of interest. You generate again the aggregated value. Then you are keep shifting your mask, and that's how you cover all those pixels in given image. And that's how you are going to get a brand new convolution. It's a first layer, you have performed that, and depending on your mask type, your size, you are performing these locality plus aggregation, and you are keep performing until the whole image is completed. And when you are keep doing that, that's where the composition comes. So this whole convolution is happening from layer to layer to layer, and that's where the more complex features or the more robust features are generated. So that is called the composition, which is the function of the function. So when you perform the composition, your features are enhancing. It means initial the feature was the basic, and when you go at the last layer, your feature is complex. That's how you start from start to end. You get to learn more about your input image. When we talk about the CNN, here is the example of convolution. Here is input, and then your layer 1, layer 2, layer 3, and finally you are flattening it, and that is your output. In this whole sequence of convolution happen, features enhancement or the complexity of feature is coming up. It means what was just a spot here is actually the complete feature is available. And that's how you are going to get the higher probability depending on which particular class your requested image belongs to. So now if we try to compare the convolution which was happening on these 2D fixed space data structure, we need to understand that how the graph really compares in that contrast. Here left side we have graph, right side we have image, and this is the text. So text is you can consider as an image format. The only difference is it's just a 1D space. Images are the 2D. Image you have pixel, and in the text you have tokens or vectors, whatever you call them. Between images and text, the position is fixed. all the time. Position does not change, and it always stay the same. However, when we look into the graph, we find some ambiguity. So very first is the arbitrary size grid, because grid size is not defined properly depending on which angle, which node you try to start your counting. Second is non-Euclidean space. We already talked about that this data structure does not fit in X, Y, and Z scale. Position and sequence is not fixed, is always changing all the time, versus compared to image and text that we already have that fixed. And finally, there is no node order fixed. We have already checked when we were walking. It could be anywhere. So ordering is also not fixed. So the walk between A to C will be two different time depending on how your random walk had happened. And one more important aspect we also have to understand is that the node order and adjacency matrix. So remember we talk about that the no fixed node order. So if we try to go a little more deeper and try to understand that, okay, what it is, how is really going to impact us, then we have to look at this thing. So here you see that this is our favorite graph which we have built, and here is the adjacency matrix. Now we are changing the node order. We are replacing A and F. F comes here and A goes there. That changes the matrix. And now this matrix is not the same as this matrix. And that is the actual problem. When you change the node order, everything changes. So there is a big ambiguity between having graph and image we have to think about. So the question comes that when we try to apply the convolutional CNN method on the graph, we cannot use the existing methods which we have already applied on image and text, because the convolution requires the grid and sequence to be fixed while processing structured data, which does not happen to see in our graph. So next, we can understand the feature matrix. Here is an example of feature matrix. Each node has these given three features. So if you would want to build the feature matrix, which will be the each node has a three features, it is very much possible that one node might have only one feature and two other features are missing. In that case, the size is still be considered as a 3, but two features will not be applicable here. So for the feature matrix, X will be equal to 6 times 3 equals 18. So feature matrix is the number of nodes times the total number of maximum features which catered across every node. So make sure you understand that feature part very well, because that's going to be applicable a lot while we are going to work with graph neural networks. Here we learn that in the convolutional neural networks, we perform the locality and aggregation. And then while we do this thing for at each layer, finally we add the composition, which is the function of the function, which helps us to find the strong or the better complex features. Now if we go and say that how the convolution is going to happen on the graph neural networks. Locality, so we got all the neighbors. So when we take the locality and we try to match the locality with the convolution in image, those are the pixels in the neighborhood. In the graph, all the neighbors available for this given node. And for the aggregation, in case of image, it was the pixel of interest. Here is the node of interest and all the neighbors. And one by one, we select all the nodes available in the neighborhood, and we perform the convolution on every node by selecting one node to another and aggregate all the neighbors' contribution to the given node. And that's how we perform the locality plus aggregation. And then finally, the composition is the layer stacking. So node embedding is the answer. That's how we could represent our graph nodes as the vector. Once we have that concept available, now we can apply the convolutional method on graphs. So now we have to understand what is node embedding. And it is a very important concept, because we made a statement the node embedding helps us to represent the graph as the vector, and once we have that representation, then it's become easier for us to perform the convolution on top of it. So left side we have our graph. So the left side we have our graph where we have seen that again and again in this tutorial. The nodes are there, node features are there, edge labels are there, everything is pretty much there, and conceptually what you are seeing here, hypothetically you can think that this is just a very small view of the graph, but this graph has tens of thousands of nodes across and connected everything. So you have so many labels or the hops. You are keep going from 1 to 3, 1 to 2, 2 to 3 to 4, 5. So in mind you can have that thing. So if we try to build the node embedding, we look into right side. So we select a particular node. So for example, let's select a node number A. Where are the two neighbors? B and C are the connected neighbors for that node. Now the next is the D is the neighbor. So that's where you see here D. The next neighbor of D is F. Here the neighbor D has the neighbor F. If we look into the C, which was C here, C has two neighbors E and F. E has the neighbor F. So depending on how many levels you would want to go, you can go level 2, level 3, level 4, level 5. So that's what is going to generate your node embeddings, and node embeddings is going to be generated for every node depending on how many levels you would want to go first. This whole space where these node embeddings are created is called the node embedding space. In this node embedding space, we are creating the node embedding for every node in the graph first. Second, the connectivity between these nodes when we are creating is connected with a neural network. It means the value of F will be converged through this neural networks here, and then value of F will converge here, and then these values of T will converge here, E and F will converge here, and then this value, then value of B and value of C will converge here, and that's what going to be defined the A, node A definition. It means lots of levels of convolution is going to happen in our graph because we are performing the node embedding for every node for the n levels or the hop. So with this representation, your whole graph, if you have 10,000 nodes in your graph, you are creating the node embeddings for every node first, every node with n level second, and then for every node embedding for all the nodes, you are performing the convolution. One good thing with this model is that now, rather than looking into the graph altogether once, you are looking into a very small graph at first for node A, node B, node C, node 1, 2, 3. So very small graph depending on how deep you are looking into the labels or the hop, you are looking a very small depth. So from the original graph, you split it into based on node embeddings, you are performing convolution on the very small graph as visible here. So node embedding based on local neighborhoods. You select 2, 3, 4 neighborhoods, so that's your locality, which is similar to our convolution in image. Aggregation, we aggregate using the neural networks the weight of each input, okay, and then composition, every node has its own computational graph. So you have whole computational graph built for your own node. So that's like a composition feature. And finally, the encoder function used to perform all three things. So you can use an encoder to perform the locality, aggregation, and composition all together. So the next image should be very clear for you. Left side is still our graph, right side is the node embeddings which is ready for convolution here. So as you see here, the features are here, weights are here, the sum of all weights is aggregated here for the F. For this F, features are there, weight is there, weight was applied, and the sum of all weights are aggregated here. So that is there. Now that is being passed into here. So you have sum of this, sum of this. Now the D, the weight plus the features, same thing here. Everything is being and everything is summed into. And finally, the sum of all weight is being pushed in or down the road, and that is where you are getting the final. And then in order to process this whole thing, the encoders are applied depending on your whatever levels of depth you have created in your node embedding locality definition. Remember, this node embedding, what we are doing is that we are doing for every node in our graph. So it looks like something this. So here you could see, this is the image I have taken from this URL. Here is our graph. Here, what we are trying to do is that we are performing the convolution, everything, and finally you are getting the final result here. All the convolution, everything converges at here, and that's where you are getting the value of h. Now, depending on every node, so you are getting the A for B, which is red, C green, then your D is blue, and then your E is violet, and the F is your pink. So all the node embeddings for every node is available, and every node has its own computational graph. So this is a very important aspect for you to understand related with graph neural network. In your mind, you should have that picture built into, because once you are going to use the GNN and try to build your graph neural network for the given problem and the given data set, this representation in your mind will definitely going to assist you. So next, we need to learn how the masses pass between these layers from all the way to the bottom. And these steps are defined, and I do have one image which should help you. So the definitions are very simple. So you have node, and node has these feature vector. So for every node, the aggregation happen for the feature vector, all the hidden state, plus all the neighboring node edges, all the neighboring node connections, so basically the degree now you can think about. So that aggregation happen, and then once the aggregation happen, the value of the hidden state is updated now, because that's a new message, and because of these connections, now that message is updated, and that value will become the value of the node. Now in the next step, some of the masses are really being moved from one node to another, and that's how the final sum will be created, which will be sum of all the message obtains from all the neighborhood from the given nodes. Here is the visual representation of message passing plus propagation. Here, this graph, what you are seeing is the extension of this graph, this node embedding. However, I have represented it in the way which we have learned a lot, where the input X and all the layers and Y. Here the input is all the nodes as we are looking into, and the message passing happen where the feature vectors and the weights, everything is being summed for the all the features, all the connections, and that level by level all that information is being created and aggregated. So sum of all features all the way, and that is what is available at the node A. And then this whole message passing is done again and again by combining the forward propagation and back propagation, which you with the help of a loss matrix. So the very first time forward propagation, all the mathematics, all the sum of features generate a loss function which send back to the back propagation, and then we try to improve more and more and more, and finally the sequence of repetition done from message passing from all the neighborhood to the main node, and the loss matrix is being updated. At last you will have the node which has all the feedback coming out from all these neighbors. So at the start, when the node A has a very limited information regarding all its neighborhood, with this whole message passing and the propagation method, now the node A can represent itself by combining the forward propagation and back propagation, including the loss function. Now these repetition will help for node A to collect as much as details are available related to all its neighbors. And same thing is going to happen for every node in your network. So now each node has enough information depending on how many levels of neighbors you have collected, and each node information can then be processed further for the classification task, similarity task, and several other types of graph problems you would want to solve with graph neural networks. What are the advantages of node embeddings? So node embedding, we already know that is a way to represent the nodes as vector. So if you take each node and look into the node embedding, depending on how deep you are going, you can show the topology, network topology of your graph. Nodes that are similar, they will have the similar embedding, because so now if you build the node embeddings, you can very easily, not quickly, but easily you can find out the similar nodes because they are going to have the similar network. And also, if you would want to predict variety of prediction, similarity, the connectivity, the feature set similarity or relationship, so those predictions could be easier to perform by using the node embeddings. You can apply for node similarity, similar nodes, link prediction. You can recommend these two or more people should be part of same group because they belong to similar interest. Node classification, like a similarity, node similarity, you can classify the nodes based on a group of type. Clustering, you can take the node embedding space, and then you can group the nodes based on their similarities. So nodes can be grouped based on common objective. You can classify the graphs, so you can aggregate all the node features and you can compare with other graphs, and you can say these two graphs are similar or not. So you can compare basically and get results out of it. You can also take a one design objective and you can classify the different graphs. And with the graph classification, if some graph is really super massive, you can break into a smaller graph and then you can match with them other graphs, and then you can understand a particular very large graph much better. So there are several uses of graph neural network. Some of those uses we are going to study next. I will be also creating this slide deck and uploading it as a graph neural networks part 2 for your reference. In the next step of our learning of graph neural network, we need to learn how to handle the data or the data sets while working with PyTorch geometric. The PyTorch geometric is a collection of variety of graph data sets which you could use to learn as much as you would want. We are going to focus on Karate Club dataset. And we will also try to use the NetworkX Python library to apply and visualize the graph wherever applicable, so we can learn more about our dataset, because this dataset is used to perform the few other GNN examples later in this tutorial. So first, like any other PyTorch related experimentation for the graph neural network, what we do is that we check the version of the torch available, and depending on that torch version, we try to install the various torch geometric or PyTorch geometric and other dependent libraries. So based on this version 1.11 and CUDA supported, we are installing these libraries specific to PyTorch. We are importing some of these important modules. Torch, we already know, NetworkX, build the graph, and finally the matplotlib to show the graph. First, we are importing the Karate Club dataset, and after that, this dataset is the type of Karate Club. So we are importing the Karate Club dataset module, and then from Karate Club dataset, we are defining our dataset objects. Here you can see that this dataset is a collection of one graph. It has 34 features. Total number of features are 34, and this dataset has total 4 classes. So if we take the dataset, the number of graphs, you might see that some of the datasets actually have n number of graphs. So depending on how many graphs are in a given data set, you can use the data set objects to take or extract whatever graph you are interested to. Second, the number of features. So this data set has 34 features. It means that each node in this data set is assigned a 34-dimensional vector. In this data set, each node is assigned a 34-dimensional vector. And each feature is uniquely defined the individual node. So if there are 34 nodes in this graph, then each 34 size vector has a one value true and remaining values false. So that way for all 34 nodes, you are going to get only one single feature true. So that's what the uniquely describes the members of the karate club. So that's like a feature of each node. And this graph holds the 4 classes. It means the 34 nodes, they belong to 4 different classes. Next, whenever we talk about the data set in PyTorch, so PyTorch data set holds the following attributes. So whenever you take a data set and you get the graph object, so remember this data set is a collection of one graph. So we are taking the first graph object and we are printing the data. So here you are getting this data object which represent X, edge index, the Y, and the training mask. So these values are defined with this PyTorch data. So these are the attributes for the data object in PyTorch. So X represent to the feature matrix, which is the number of nodes and number of features. So number of nodes are 34, number of features are 34. The edge index. So the graph connectivity, when you are connecting, so you have 2 times the number of edges. So 2 of number of edges. So actual number of edges are here is the 156. The next is Y. So the target to train against. So remember, if you are performing any kind of machine learning, so this Y can be used for the target to train. So there are 34 of it. And the training mask. So training mask, you might see the validation mask. You also see the test mask. So train, test, and validation mask, I will not explain in this Jupyter notebook. I have another notebook which I explain this in details. So currently, just looking into our karate data set and very first graph, we could see that this data has the X means 34 nodes and 34 features, and total number of edges are 156 here. So all the node labels are in Y. So from data set, we came to data, which is our graph object, and now we look into what is inside the graph. Here we could see the total number of nodes are 34, total number of edges are 156, the average node degree means how many connections are available for every node. So this is the node degree. It means average. It means every node has about 4.59 connections coming to it, has isolated nodes. If in this graph, are there any node which do not connect with anybody? So there are 0. Has self loop? Are there any node which has the self loop to it, which is none? Is this a directed graph? No, it is not a directed graph. Is directed, is false. Is undirected, true. So this is the undirected graph. Next, using the data, we can look into if there is any edge weight defined, and as you could see here, there is no edge weight. And so you see here, we are assigned the training mask. So training mask is assigned here. So the total number of training nodes, so the training mask of sum. So if you look into here, we look into the training mask, we can see that there are 4 nodes out of 34 are the one which is available for the training nodes. It means that out of 34, 4 nodes are available for training. Training node label rate, total number of nodes versus how many nodes are available for training. So it means that for given graph, only 12% of the nodes are available for training. Even these 2 concepts we are going to study in the next notebook. This is more about understanding the data set, and if you understand this karate club data set, you can use the same learning up and you can apply to any other data set. It is very useful for you to understand the data set first before you try to learn the PyTorch geometric, and with any of the available data set. So here you look into, this is our data. So we are printing the data, and then when you go look deep into the data this node stores, you are going to get quick details. So you see that there is a X. This is the X defined. So 34 by 34, that's your X. Then you have edge index, which is like a 2 times 156. So 2 times 156. And if you look into it, is pretty, the way it is really defined is that 00111. You can get this edge index. Then it comes to Y. And here is the label for each Y. So you could see here that all 34 labels are defined. 111, 333, 1. So remember, it talks about the classes. So we will look into that classes. And finally, the training mask. So as you could see here, out of the training mask, everything is false based on this 34 your Y. Only you are seeing 4 out of 34 are training mask. So looking into this node stores, that helps you to actually see what is inside here. Next, you take this data and convert to dictionary, and which just takes this whole thing, and then if you would want to process by some other JSON processor, you can export it to dictionary and you can process it if you just want to write some more code to represent your data set. So this data, even if you take your own data set, you convert into a PyTorch data set, then you have all that functionality available to you. Next, we want to just use these JavaScript display method so that we could represent the viewport or the view set for our cells. Here is our karate data set. So now we look into the edge index. If we try to take the edge index, we try to print. So remember, these are the two 156. So here is a 1 for 156 and 2 for 256. So 2 of 156. And if we try to convert this to the tensor, here is our tensor representation of our edge index. So that should be more clear to you that when you are looking into all the nodes from 0 to 33, total 34 nodes, you are going to get the edge index very quickly based on tensor. So this edge index, the formatted of the tensor, if you try to represent your graph, visualize it, you might have better understanding of it side by side. So now the number of classes. So if you look into the graph, it has the total number of classes are 4. So if you say there are 4 classes, how you can figure it out there are 4 classes? In order to get the classes, you look into the Y. So Y, if you say, so Y is the class definition for your nodes. If you look into here, this Y is the target to train against. It tells you that within your graph, what are the labels for your nodes. Now you have 34 nodes, and here you can see that your Y has, out of 34, this shape is represent some of are 1, some are 3, some are 0, and some are 2. Then we look into the node features. There are 34 node features. So now your question will come that where are those features? And if you remember the data X, it's the number of nodes and the number of features. So we can look into the data.x, and here you are going to get the features. So if you see here from 0 to 33, each feature is representing the unique identity of each node. So 1, rest are 0. Second, 1, then rest are 0, and slowly very last one is 1 and rest are 0. So if you take these 34 features, you can very quickly say that yeah, each feature represent one unique node. That you can look into, this is X, and this you can look into the 33. So all are 0, only 1 is 1, 1 is 1, and rest are the 0. So hopefully that clarifies the features part of your data set. Now we are visualizing the graph. So here is the NX drawn NetworkX, and we are passing the graph, and rest you can see here that is spring layout with the label false, node color, and this is the color map. We have already seen that in our previous Jupyter notebook when we talk about NetworkX visualize graph method, which takes graph and you need to provide the color, the coding. Now we are taking this data, which is taking to data set 0. The first element in the data set is our data, because there is only one graph. And what we are trying to do is that we are trying to say that 2 undirected is true. And we are creating the undirected graph. And I just want you to put little more emphasis on it. So we are taking it and we are saying 2 undirected. So make sure it's an undirected graph. So it's a karate undirected graph, and we are labeling the color based on data.y. So data.y is representing 4 classes. It means when the 34 nodes will be created, they will be represented into 4 group of classes. So as you could see here with this graph, we are getting 4 classes: light blue, gray, green, and yellow. If you do not pass this color, or you just take this graph G just for example here. So here we are going to do the nx dot draw. We have data, but this data is not in the NetworkX format, because we are already using this to NetworkX to convert this to data and data. So we are creating this NetworkX draw and passing the data in the form of NetworkX. And here you could see that this is the directed. But if you would want to make this undirected, we have to call this thing as to undirect equals to. For that reason, we have added undirect as true. So we could see in this way. If we call this to undirect equals true, same graph, and as you could see here, all the nodes are just being represented as a one single class. For that reason, we have passed this data.y, so the nodes can be represented into 4 different classes, or whatever number of classes are available. Next, the karate is still the undirected graph. So we can see the number of nodes. So there are these number of nodes from 0 to 33, total 34 nodes. And now we are rendering this graph with 4 classes and then nx.draw. And as you could see here, we are getting the same graph which we have created here, but here we are getting the graph with the labels, the labels plus undirected edges. Undirected graph, number of edges, and here you can get the edges. So as you could see here, there are total 78 edges, and these are the edge view. So 0 to 1, 0 to 2, 0 to 3, 0 to 4, 0 to 5. Now, if you remember, so here is your given edges in tensor format, and it shows that how the edges are created from source node to target node. And 0 to 1 means node 0 to node 1 is a connection. Similar to that, there is a connection between node 30 to node 1, or all the way depending on how the node to node. So if we look into that, how many nodes are connected with how many edges are there with 33. So you can see here 33 to all these connections are available. We can look into our image, try to look into 33. Now the undirected graph degree, here you could see that total number of connections. So 0 is 16, node 5 is 4. So if we look into this, we can see that node 33 has 17 connection, node 32 has 12 connection. We look into node 25, which has a 3 connection. So this labeled graph, node 25 has 3 connections. If you find 25, we could see the 3 connection, 1, 2, 3. So this graph is small enough to handle and big enough to do the machine learning. For that reason, it's a really very ideal graph for us to learn not only the data set, but also perform the machine learning. So you have got the total number of nodes and their degree. So that should be clear to you. Now what we are trying to do is that we are taking this data object, converting to a NetworkX object and calling it a directed graph. It means we are not passing to undirect equals true. So this became a directed graph. And as you could see here, the directed graph does not have the attribute node. So we are taking this directed graph, we are rendering it, and now you could see here that this graph has the directed edges to it. So we could check our node 25, 3 edges are coming to it. And if you look into the directed graph, because initially this is the undirected graph, but once you convert to a directed graph, the same edge which has no direction, now it's connected with both ways. So it's became 2 times of the edges from the undirected one. And that's where we are going to get the edges here. If we try to perform it, now you are getting 156 edges. And reason is that because if you look into previously, you have got 78 edges here. But because you took the same graph and you converted into NetworkX and you said it's a directed one, now you are getting 156 edges. And if you look into the degree and we look into the 25 node here, now the 25 node has the degree 6 because same node is two-way. So you are getting 2 times. And the last 33 is a 34 because it was 17. So you should have a very good idea about when you take a graph, play with directed versus undirected, how situation changes. Now we are taking the directed graph and representing it into the matrix. We take the undirected graph, they are still going to be the identical, the matrix representation of those graphs. So you have seen that how the NetworkX manage the directed versus undirected graph. If you do not explicitly say that A to B but not B to A. If you do not have, you're just changing the graph, everything you have seen how it works. So the PyTorch geometric does not distinguish between the directed and undirected graph. It deals everything that is directed to start with. So for example, if you say AB, A to B, it is not B to A right now. However, once you say it's an undirected graph, so what PyTorch does is that as soon as you say this is undirected graph, it's automatically add a reverse edge to that directed graph. So now the directed graph, it was very clear it's A to B. And if you say no, it's not directed, it's undirected, it means it's automatically adds the reverse edge. So A to B was already there. Now B to A is existed there. And that's how it treats the undirected graph. So now this Jupyter notebook is also saved into the graph neural networks folder of the Steepworks repo for you to follow. So before I start this Jupyter notebook, because we are going to perform the graph neural network, which are resource intensive, and our Colab may not have enough resources, so I will try to enable the GPU also in this Colab notebook so we can get little more resources in order to perform our example. So first thing what I will do, because we do not need to have these runtime available, we can disconnect them. So they are no longer using the resources within my account. This one I could terminate it. Karate Club data, so only we are interested into GNN experiment with Karate Club. So that's session is only we really needed. Now we are going to check the resources. As you see here that we only have RAM and disk. And for this Jupyter notebook, we are going to change this runtime type. And here we can say if available, we're gonna be using the GPU. So even when we are not upgrading to Colab Pro, still using the cheap and free method, we could get the slice of GPU along with CPU. So let's use this. So now we have RAM and GPU available for our project. Then we can start our experimentation. So first, I'm just making sure that we do have the PyTorch geometric library installed based on the PyTorch version available in this machine. Next, we are importing the Torch, NetworkX, and matplotlib. Then we are importing the data set, and here is our data. So up to this, we have already covered in previous notebook. Next, remember, we missed this training mask study because when we were studying this data set, we decided that we will look for the training mask later. So now it's time for us to look into the training mask. So here is the training mask. So if you look into data stores, this is our training mask, which shows that true. So there are like a few true, 3 and 4. There are 4 trues. It means that out of these 34 details, we have 1, 2, 3, and 4. It means 4 of these items can be used for the training. It means labels are given. Rest of the labels are not given for us. So only 4 nodes have the mask value sets true. It means that 4 out of 34 nodes have the community or the class assignment. So remember, we had 4 classes here. We can say that if we are trying to perform a machine learning or the neural network based prediction that where remaining nodes should go, we can only use 4 as a training mask. The rest 30 cannot be used. It means that out of these 4, each one belongs to one community. So how you can validate it? So this one belongs to this one belongs to fifth, 1, 2, 3, this third, then next one is belongs to here, so which is should be part of 0, and then rest should be part of 2. So it means that each mask, training mask, is belongs to one of the 4 given community. If we can use them for the training, it means out of 34 nodes, we have identifier for each one type of node. Rest we need to train based on these 4 given nodes. We do not have the validation or the test mask. So some of other examples we are going to follow in this tutorial, you will see that validation and test mask is also available. So what is the GNN objective? So our objective is that we have 4 nodes based on community assignment. So we need to assign the remaining 30 nodes, which particular community they should belong to. It means our final output should be that all 34 nodes should belong to 4 different community. So for that, GCN, Graph Convolution Network, is being created for ourselves. Here we are using the GCN convolution type, and there is 3-layer network is being created, and feed forward mechanism for our network is decided here. And finally, we are applying the linear classifier. So we could classify which particular node belongs to which community. So this is our model. So we have defined our model. This is the 3 layers, and then finally the classifier is used as a linear here. So model is GCN, and now if you look into this model, we haven't trained anything at all. We just took this model, fed these 34 features. So it's a 34 times 34, and we are also sending the edge index, means which edge is connected with which. And based on that, we are getting the edge. So embedding space. So you are getting this 34 of 2. Now let's see what is edge. So this is the edge, which is the output of this model is look like that way. Now we need to visualize the embedding. It means the edge which we have just created just here. You see that no training, nothing else. We just use this model definition. This is our model definition, and we have fed the data into. And based on that, we are defining this visualize embedding, where we are passing the edge, which is the result of this model type. And if you look into here, written out is edge. So out is the classifier edge. So this is the classification of your edge. And now we are also creating another method called the visualize the tSNE. I will just run it, but I will explain you little later when the method will be called. Right now we are not calling that. So here is our data.y. We already saw that 4 classes divided into 34 different nodes. So we are visualizing the embedding by passing the edge, and our color coding will be based on data.y. So here you could see that 4 classes are divided, and just looking into preliminary without even graph neural network training, we could say that these communities are isolated. Some of this is very isolated. This is really little more community. There is another community, but few things are mixed into in this area. If you look into, if we take this area, hide it, then we can very clearly see the 4 different communities: yellow here, gray here, blue here, and green here. It means that initial representation of our network model is able to give some basic results about how the graph nodes are distributed across community in this whole node embedding space. We haven't tried anything. Now we are creating the whole training method. So here is our training method we are creating, and here you see that this is just the representation of our content. So I will split it piece by piece. Now we are defining the model here. Now we are defining the loss matrix. So this is our cross entropy loss. So this is our matrix, and then we are setting up our optimizer. So step by step we are setting up our optimizer, and there is our learning rate, which is 0.01. So based on convolutional neural networks, so just like running the neural networks, most of these things should be very easy to understand for you. Now I have just added by myself, because the reason why I have added this, because when we are going to perform this training, you are going to see the embedding step by step. So we are going to train and 400. So you see here that what we are going to do is that when we are going to perform the training, after each iteration, you are going to get the visualization of the embedding. It means after that many training epoch, you got this embedding, then this embedding. So very last embedding I have saved, so we can represent last embedding, and we can see that how far we went from level 1 to level last. So this is the final embedding. Right now is the first one, but at the last became the last one. And here is our training method. So this is our training method. Optimizer 0. So all the gradients will be set to 0 here. And here's the model. We are passing data X, and the edges, as you see here, out and edge. And then here is the loss, and that is really going to be called here. So here is the, you see the training. So it's going to generate the loss and edge. So loss and edge, and edge is your model when it is returning single forward pass. So I think that should be okay for us. So let's define the train, and we are going to perform the training. So when this training will start, you will see that the embedding images will be displayed for you. And as you see here, that as we are growing from step by step, this is the initially we have started. Let me move a little bit up. Loss is 1.4324. Then loss is reducing. The new community displacement for all the nodes is being created. As loss is going slowly down, epochs are growing. So every 10 epochs, you are seeing the locations of this community. And as we grow further and further and further, as you see here, that green, blue is being separated. More and more separation is happening here. And finally, when we hit very last, our loss is getting even more smaller. And at the very last, our loss is 0.0246. And here you could see that yellow, green, just yellow here, green, and then these are all the blue and the gray. So the community separation or the clustering of the community depending on our target class. Remember, we had a one training for each type, the class type, and we were able to perform this separation nicely. Now this was our last image. So that's the reason I just wanted to, because this way is easier to hold ourselves, and we can see this was the last. And if we look into before training, it was the first. So this was the first when we start, and after the neural network we built, this is where we got it. If you want to visualize the tSNE, I think you should know what tSNE is. Based on that, this is the distribution of our nodes. So here you can see yellow, green is there, blue is there and gray is there. So it's a tSNE visualization of the same. Okay. So now the result, so we had a 3-layer graph convolutional network, and it managed to linearly separate the communities and classifying most of the nodes correctly. If you would want to evaluate the model, here is the evaluation. You cannot get the performance because we had no way to get the testing data, so we could actually check that given the test data how many communities are evaluated correctly. So here is that, and then because there is no test mask, so we could not get. Now if you just want to go a little more deeper into the model, so here is the model, these states. If you see that these are the different, so you can look into where the model weights are, where the biases, all that details for each layer. Model type, it tells you the definition of model. Rest is like a model, details are available for you, parameters. And finally, if you would want to save this model, so here you see that we are saving the model into, it's like only the dictionary as a state dictionary versus the model. So we are saving these models into separate format. So we have saved this. It means that if we look into our Google Colab file system, here we could see these two models available. If you would want to visualize these models using the Netron or any other utility, you can actually see them also. So let me download them. And I always suggest if you are interested in finding out that what's the size of these files, because sometimes if you see here, you cannot see those sizes here. You can say in the content folder, and that gives you that Karate Club full is 7.5K and Karate Club, which is around the 3.3K. So if you are new to Netron, it's an open source, a model visualization utility, very popular. I'm importing the Netron. Here you could see that these are the two models which we have just downloaded. So first I will visualize the model, which is just using the dictionary. This is just the definition of our module. But if we choose and we try to visualize this, here is our graph convolutional network. And you see this is a 3-layer, and 4th layer we are just generating the final result. So this H5 format, when we download it, does not have rich information for us to visualize using the Netron library. So this experiment is completed, and we are going to save this notebook, and I will also make this Jupyter notebook available in the same place. Now you can follow up the tutorial and you can run the experiment by yourself. So now in this last part of our tutorial, I will be taking one example directly from PyTorch Geometric and run it, and I will explain you step by step, because during this whole tutorial I have explained you so many concepts. It means it becomes very easy for us to take one of the example available in PyTorch Geometric and we can understand it much more clearly. So we can look into available tutorials. So here there are lots of PyTorch Geometric tutorials available. So this tutorial, which is the node classification with the graph neural network, is the tutorial which I will be following. And what I have done is that I have already downloaded that tutorial, and 1 or 2 places I commented and I added 1 or 2 extra content to it, because that become easier for me to explain. However, if you would want, you can just take this tutorial, you click here, it opens the Google Colab for you, and you can run by yourself. So now we are going to start this example to node classification. So that's why I named it example to node classification, which matches with this tutorial name. Let's add support for GPU also. So we can look into the view resources. I already enabled the GPU. So it means that we will have little more juice for ourselves to run this experiment. Because first thing, what I am just making sure that our machine has the PyTorch Geometric correct version installed based on the Torch version available in this Google Colab environment. We are importing the NetworkX matplotlib and the sklearn, because we want to use the tSNE visualization. So here we are using this visualize function is revisualizing the tSNE. Next, we are using this data set. So we have the planetoid data set, and we are reading the data set and by normalizing the feature. It means those are machine learning ready features for the data planetoid. So if you take this, look into the data set and you search for planetoid, here you will be able to find the data sets which we are pulling into. You already know that we are importing the planetoid and normalized features, so we could read data set correctly in normalized, so which means it's ready for deep learning. So data set is being downloaded, name is Cora. So this is the Cora data set from planetoid. Once we have data set, we can learn more about data set. It has one graph, 1433 features available in 7 classes. So we can get the data set because one data set, so data set 0, first one index, so data, this is our graph. Now if we would want to see what is inside data, here is your data, so X. So you have features 1433, so that many nodes you have, edge index 2 to 10556. So these are the number of edges. CO format, the list of our targets. Training mask 2708, validation mask 2708, test mask 2708. So total number of nodes you have. So at this point, if we try to print this, we are getting 2708 nodes, that many edges, the degree almost like a 4 connections per node, so degree. Total number of training nodes are 140. So you take data x dot training mask. Here you are getting all the true to true. So out of this training mask, out of 2708, 140 values are true. So that's the training mask for you. And 140 out of 2708, so it's about 0.05% is the nodes which have training. Isolated nodes, no. Self loops, there are no. Is undirected, true. So these three should be okay. So that is already been explained here, but I have walked you through. Okay, so now we have the validation mask and we also have the test mask available. And then reason we are using the normalized features, because that's why our data set will be ready for our machine learning consumption. Otherwise, if you have used the neural network based training to solve any transactional data, you see that you need to normalize those values so that they are being fed into the neural network. We could have visualized this data. Here is our visualized graph. It will take some time because this graph is quite big. So we are trying to convert this graph. We will choose as it is. Okay, data.y. Let's visualize this graph. So here you could see that this is the network visualization using the NetworkX. Now we are going to train without using the graph neural network, just simple the multi-layer perception network MLP. And here you could see that there is a definition of 2 linear layers, and here's the feed-forward network. And this simple MLP is defined first. Here is our loss matrix, and here is our optimizer. Then training is done. Clear gradients, you can see model is passed. All the data.x is passed here. So you see here data.x is passed. And let's perform the training. And training is done. The initial loss when we started the training was 1.9, and by after 200 iterations we have achieved 0.038, and the test accuracy is, because we have test mask, accuracy is about 59% for this. And here what we are trying to do is that using the 140 nodes network, we are trying to perform the node classification for remaining of the nodes. So using the test mask, we can figure it out what's the accuracy. Now we are using the graph neural net, and here we are defining, you see there is a 2-layer convolution, so GCN convolution. So this is our definition. Here we are instantiating the graph convolution network to model, and here is our model, 2-layer. And now we are visualizing this model using the tSNE. So this is the tSNE function we have created, and we haven't even performed any training yet. So at this point, we are creating the tSNE graph before even training is completed. So here you could see this is initially look like, and these are 7 dimension, because the initial data set when we studied early, we found that there are 7 classes. So all these 2700 something nodes, they are belong to 7 different classes. So what you are seeing here in this graph, this is the layout of all those nodes in 7 different classes. Training has started and we are using 100 epochs. If we just want to go for 200, for example, we even after 200 iteration, we even get lower loss. It means the accuracy for our model is 80%. Just for an example, if you would want to go these 400 iterations, 400 accuracy 0.82 8020 to 8060. Originally, it was 59% with multi-layer perception network. Now we have 80%, so it's a 20% increase. So because now we can visualize the tSNE by our result model, and after the training, now you could see that all these 7 different classes, 1, 2, 3, 4, 5, 6, 7, they all can be is very nicely distinguished using our node classification model, where we have used the graph convolutional network. So after our model was able to clearly classify the 2700 nodes in 7 different classes, let's learn the GNN Explainer module. It is part of PyTorch geometric. Here we will learn how we could use the GNN Explainer. So let's see what GNN Explainer does. First, let me show you what it does. Then it will be fairly easy for us to understand. So we are importing the GNN Explainer, and then we are taking this model which we have just created earlier. So this is our model, and using GNN Explainer on that model so that we could train. And once the explainer model is trained, we can learn that for a particular node in given graph. So for a particular node in given graph, how the prediction was possible. Let me build this explainer model. So it is defined. Now we will choose the node, which is something, maybe node is 100. Now explainer.explain node. So we are taking for the node 100 based on x and age index, based on edge and age index. Let's generate the node feature mask and the edge mask. So this training has been done. Now these 2 values can be used to visualize that what was the factors or the feature set which were important to predict the node number 100 classification. And that's where you see, so explainer has the visualized subgraph where we are passing the node IDX, which node in question, and we are passing the age mask and age index, and the y, the classification of the data which we already have. So that gives us ax.z, and then we are going to visualize it. So let's try to use the node 1. Training is done, and here is the visualization. So let's see edge index. So let's print the tensor of edge index to edge index of t. So 0 to 66633, 0 to 1862, and let's use the node index 0. Visualize. So 0 connected with 66633, 0 connected with 1862, 0 connected with 2582. So these are the 3 connections we have. So that's how the CNN Explainer will help you to walk through whatever edge you are interested into. So GNN Explainer, as I mentioned, that is part of Torch Geometric. You can learn more about it, but using the target node index and the given graph where you need to provide the X, the features and the nodes plus the edge index, you can find the path and you can understand that how the prediction was possible depending on the connectivity for a given node. So this Jupyter notebook is also ready for you. I will save this Jupyter notebook to the same place like other Jupyter notebooks. So these 4 Jupyter notebooks which we have covered in this tutorial, they all are available here, and the part 2 PDF I will just upload after this completion of tutorial, so that will also be available for you. So let's recap what we have covered in this tutorial. We started with the theory part of graph neural networks, and we understood the adjacency matrix, incidence matrix, degree matrix, Laplacian matrix, and a way to build our own graph and visualize it properly with all the mathematical representation of graph which we have learned. After that, we also learned the graph neural network concepts, the role of Laplacian matrix, the image representation, how the convolution happened in the image by combining the locality, aggression, and the composition. And then we applied the same concept over the graph, how the locality, aggregation, and the composition works on graph. We understood the example of node embeddings. We also figured it out how the convolution can be applied to the node embeddings. That's there. And finally, we understood the concept of message passing with the propagation in a graph. After that, we studied more higher version content in the NetworkX with reference to graph, how to get the incidence matrix, degree matrix, adjacency matrix, Laplacian matrix, and how to visualize your graph in much more informative way. After that, we studied the Karate Club data set. So the way we understood so that we can prepare ourselves to learn the PyTorch geometric very well, because there are lots of data sets to play with, and understanding how to handle the data in PyTorch geometric helped us to perform the GNN experiment on the Karate Club dataset, which we have completed by the node classification, and we have also performed the node classification over the Cora datasets, and we visualize it properly. And at last, we also used the GNN Explainer to figure it out that how the prediction or specific related to a node can be explained with the help of GNN Explainer. All the content we have covered in this tutorial is available at Graph Neural Networks folder of DeepWorks repo. So that's all I had for you in this tutorial. I hope you have enjoyed it. If you like my content, please subscribe it, share it. I do appreciate kindly. Once again, thank you so much for your time, and I'm going to look forward to see you in my next tutorial. Until then, thank you so much.